Okay, so the second, let's just kind of go through all the data that are reported. And we'll start with the oil properties. So the oil density is reported. But this oil density is not measured directly, okay? It's calculated by what I would call a kind of material balance. Okay? And the way it's done is that this final residual oil that they measure here, they measure that density, and they'll also, in connection with the, well, for various reasons, they'll also usually measure molecular weight, but certainly density they'll measure of this final oil. So we'll put that in pink. So then they'll calculate the density at any higher pressure as the mass they account for at that particular pressure that's in the oil divided by the oil volume, which is also changing with pressure. And the mass is calculated as the starting mass at the end of the experiment. There's a residual mass. Of course, that's just the volume at the end of the experiment times the density, plus all of the gases from the end to whatever pressure, whatever gases were released. Okay? So basically the gas volumes expressed as a surface gas volume, that would be the same as the moles, if you will. Divided by okay, we'll just put it that way. Actually, I'm not even going to do it this way. We have these moles that are measured, being removed each stage, and it starts at the final stage and goes to whatever particular stage. Let's say this is stage J. And it's basically all of the gases that were released from stage J and down. So it basically would be J plus 1. So the gases released starting at J and then further down. So these are the moles that were removed. And if you just multiply that by the molecular weight of that particular stage, that'll give you the mass. And then just divide it by the oil volume measured at that particular stage, J. So it's calculated by this material balance. So basically, they're measuring, they're basically measuring this by knowing the oil volume and its density. They measure the gas moles removed each time. They measure the molecular weight of each gas removed, and they're measuring the oil volume at each stage. So all of these are measured quantities, and of course, the fact that there are some experimental uncertainties in each of these data means that there's going to be some uncertainty in the composite term of density. But in general, this material balance is quite accurate. So we can expect this to be typically within 1 to maybe at the worst 3%, just because of material balance errors. But I would say in general 1 to 2%. I'll step out on a limb and say that in general it should be in that range of accuracy. But it's seldom a direct measurement of density with some high pressure density meter. So. Okay. The other oil property is oil viscosity. Now, the way the oil viscosity is done is that the lab runs a separate, let's call it a parallel, differential liberation test that's only designed to measure the oil viscosity at each pressure. In other words, they have basically to get oil viscosities. Okay, so it's a piece of, it's kind of like a PVT cell, but it's just, oh man, it's a big steel container with a hole drilled through it. Okay? And then there's a metal ball in the container. And they fill, basically there's kind of a metering here and a metering here. And they'll basically, this is at reservoir temperature and at various pressures less than equal to the bubble point. And each time they'll lower the pressure, they'll remove all the gas from the container, and then there's a kind of a magnet here. They'll release the steel ball. It will roll down the hole through the oil, and the time it takes, the density, basically you have to know the density of the density difference between the ball and the oil. Basically, you need to know the oil density, and together these two here give you the oil viscosity, typically within somewhere between 5 and 15%. That's about the best you can do. It's called a rolling ball viscometer. Okay, it's just a big steel thing that's got a hole in it. You fill a cylinder in it, and it's got oil in there and a ball, and the ball rolls down. They'll lower the pressure, get rid of the gas. They'll redo the experiment and so forth. So this gives you viscosities at a set of pressures less than the bubble point. Now these pressures may not be the same pressures as the volumetric DLE experiment. Okay, so these may be not equal to the pressures in the actual DLE test. So I think these are the only properties of the oil that are measured. The oil volume directly, and the oil, the final residual oil density here. And in a few occasions not very often, you may measure this residual oil composition. Okay, that may be measured as well. So effectively, it's the oil volume and the oil viscosity that are directly measured. Oil density is calculated by this material balance. Okay. Any questions? So on the gas side, they have these moles of gas removed that probably will be converted to a, using 23.68 to a gas, standard gas volume. And then what's actually reported, it'll be one of two things. It'll either be the incremental gas over the residual oil volume, or it may be a solution gas-oil ratio. And they may actually report both, but and this solution gas-oil ratio would be what we will call RS differential at a given pressure PJ, and that's going to be the sum of again starting at the end of these things here, divided by the residual oil volume. So that's, so maybe this would be a, what we would call delta RSD, kind of a, just a stage to stage incremental. So it's one of these two. But the quantity that's really important is not reported. Okay? The quantity that really makes a difference is how much gas comes out of solution from the bubble point to some pressure, right? That's really what's important, because that forms the gas saturation, and the saturation affects the mobility, and the mobility. So really, the important quantity is really how much you have of gas in solution. This is our solution at the bubble point, minus the gas in solution remaining at some particular pressure. This is the evolved gas. Okay, that's really the important quantity. From the bubble point to some lower pressure. The key thing to note is that what's reported is reported to this residual oil volume. And what's important is that they may, in the lab report, they may just write this as RS. And all those equations in all of the books that you'll be using and reading as reservoir production engineers, where you see RS, you don't want to use this quantity directly. Okay? So the engineering RS is not equal to the RSD. So don't, again, use this directly. Or else Standing will turn in his grave. By the way, he passed away about, I think it was 3 years ago. 96 years old. Okay. So that's on the gas removed. The gas density, we need that. But basically this Z factor is reported, but that is being calculated as pressure times the volume that was removed divided by the moles that were removed, gas constant, reservoir temperature. So what we actually measure is this, this, and this. Of course, if you want density, okay, let's see, 6. Wait on this one. They report gas molecular weight or specific gravity for each removed gas. And then they usually don't report it, but they may. You can certainly calculate it if you want the density itself just by this being a function of pressure. Pressure is a function of pressure. Gas molecular weight is a function of pressure. Z factor, function of pressure. So you have 3 sources changing the density. The gas composition expressed with the molecular weight, the gas composition expressed with the ZG, and the pressure itself. So both mg changes because the composition of the gas will change from stage to stage. So this may be reported, as may the composition from the DLE test as a function of pressure. So that may also be reported.
Do you only use the general gas equation, or do you use other relations in state as well? Or is that used
For the gas equation used for what?
for calculating the density, for example?
Yeah. This equation is general. I mean, even if it was an oil, but you'd have to have the Z factor of the oil. But yeah, I mean, this equation is, there is no other equation really to use for gas. Yeah. All right, so that basically gets us, I think, to the end of the reported data for for the differential liberation test. Are there any questions? So we've got, you know, it's so much for that. Okay, so here we've got the schematic picture of what we already talked about in the DLE. I thought I would just go in and select excerpts from a PVT report for differential liberation, and we can kind of see where this is a plot of this differential solution GOR versus pressure. You can see that it's decreasing, and basically the difference between what you start with and what you have it in solution, that difference would be your gas that has evolved during depletion. This is the differential oil formation volume factor, BOD. It's the barrels of oil at some pressure divided by the final residual barrel. Why does it not go to 1 here at 1 atmosphere, or 0 psig is 1 atmosphere? Why does it not go to 1? This, as we talked about, this thing here represents oil volume at pressure divided by a constant residual volume. Okay, that's the BOD. But all of these points are at what temperature? At reservoir temperature, including this last one. But this is at standard temperature. Remember that was shown up here. This oil volume residual is at 60 Fahrenheit. So the shrinkage from here to here is the difference between 1.0, looks like about 7. So there's a 7% shrinkage going from whatever the temperature is here, I don't know what it is, down to 60 Fahrenheit. So it's not insignificant. It's going from reservoir temperature to standard temperature. Okay, so that's, let's see, I'm trying to find a table. This is the oil viscosity measurement. Okay, this is the bubble point, saturation pressure. the oil viscosity here. Okay, and you can see they also measure viscosities at pressures greater than the bubble point. And the viscosity is increasing. Why would it be increasing? Well, you have the same amount of liquid, but it's the liquid's getting heavier, and the viscosity has a lot to do with how these molecules are, in a sense, reacting to the shear stress themselves and against what. So it's kind of like the shear stress amongst the molecules themselves. Well, as you get higher and higher pressure, you're compacting us. The ceiling's coming down, the walls are coming in, and it's getting harder and harder for these molecules to move around where they want to be. So it has a huge effect on the viscosity, even more than on the volume. Because if I'm getting scrunched in with you guys, and I want to get over there, and you guys are getting them in my way, the one thing is the feeling of claustrophobia. The other is, how the hell am I going to get out of here? Which is the viscosity part of it. Okay? And the reality is that, yeah, it's becoming more and more dense, but the other reality is that it's becoming much and much harder for me to get over there to the door, to have mobility. So the molecular mobility is affected. And so you'll see a bigger change in the viscosity than in the density, typically to some power of as much as 4. To the 4th power. In other words, viscosity here is approximately to the power of, to the 4th power of that. Probably can't see that very well. Now, why is the viscosity increasing so much below the bubble point? The pressure is getting lower. The oil composition is changing. Okay? The light components, methane, ethane, propane, are lubricants. That's the way to think of them in terms of viscosity. If you put methane, ethane, propane into an oil, the more you put in there, the more it's like a lubricant. It makes it flow easier, the oil. And what's happening is that as you're moving up here, you're losing your C1 to C3 lubricants. I'm not sure what the term is in Norwegian, lubricant, but Viscosities reducent. What do you call it? Smoothing, yeah. It's kind of smoothing. So you're losing those components that are making the viscosity low. Therefore, the viscosity is increasing, and so that's what's going on there. Okay. But for practical purposes, you can also say that the viscosity here is also certainly proportional to the oil density to some power. But it's not just, you don't have the same components that are behaving differently, but the density is changing for another reason. But I like to think of this viscosity increase as you go below the bubble point as being a result of the loss of these light components lubricating the oil, making it less viscous. Okay, so then let's go see if we can find some other stuff. Okay, there's the main table. Fetch that in. Okay, so this is the table here. We got our pressure, pretty clear. Solution gas oil ratio, R SD. There's an asterisk to the barrel here each time. That's to make sure it's clear what we're talking about. I don't know where the asterisk is. Barrels of residual oil at 60 degrees Fahrenheit. Relative oil volume, that is the BOD. Here we've got the oil density, gas Z factor, gas specific gravity. Okay. And then we have a couple of other columns that we have to figure out what are they. Some labs report these other columns, some don't. All laboratories will report RSD, BOD, oil density, and gas gravity. But these are kind of optional, and you know, we got to figure out what they are. Any questions about this table? You can kind of see that, you know, basically you come down to here. This here is at a double asterisk at 60 degrees Fahrenheit. No. Okay, so I'll just it's called relative total volume. So what this term here represents, and we usually give it the symbol T. That's defined as the total volume over this residual volume. So that would be the oil volume plus the total gas volume of all gases released. Kind of it's all of the gases released from bubble point to the current pressure, but those volumes are expressed at the particular pressure of interest. We'll come back how to calculate that here in a second. Before we do that, we're going to talk about this, which we're going to call BGW. The W part we'll learn when we study Chapter 7, the wet gas formation volume factor. That is defined as the volume of gas, that's on pressure, over the volume of all of that gas at standard conditions, under the assumption of no surface condensation. That means all of the gas that you start with at pressure ends up being a gas at the surface. It's usually a wrong assumption, but it's still a term that we use. And that can be calculated simply from this equation. Here. So in essence, it's just a translation of what's being reported otherwise, the pressure and the Z factor. And now that we have this term and this definition, we can actually calculate this term here, evaluated basically from bubble point to the particular pressure of interest, and evaluated at that particular pressure. So that'll be the sum from K equals the first release of gas is in the second stage until a particular stage J. The moles of gas that have been removed, converted to standard gas volume, which would be the 23.68 number, for example, or 379, depending on your units. That kind of represents your surface gas that's been released, times this BG W evaluated at the pressure of interest. No matter which stage K you're looking at, but it's always being evaluated. So you're taking basically how many moles were released, converting it to a volume at this particular pressure, PJ, each time, and adding all of those volumes together. So anyway, that's how the laboratory calculates this term here. BT differential. Okay, so that's for this particular. This is a core lab report. The Schlumberger reports, the Weatherford Laboratories, what used to be ResLab report. ResLab was just to give you more time left. ResLab is it used to be only core labs. Okay, and then other labs started popping up. D.B. Robinson. In Canada, it became a commercial laboratory. Robinson was one of the students of Katz, who was the professor standing up in there in Canada. They ended up being very famous for their laboratory equipment and procedures, laboratory procedures. They were bought out by Schlumberger some years back. There was a company that came out of Trondheim, started by Odd Hjelmeland, who was at that same course with me back in '79, who developed a core laboratory company called ResLab back around 1988 or something, I don't remember. That went from being just a core lab to being a PVT lab also. They bought some proprietary equipment and design from Syntef maybe 12 years ago for mercury-free PVT cells. And that deal with Syntef took 10% ownership of ResLab, which was sold about 5 years ago to Weatherford Laboratories for about $100 million. So that 10% paid off for Syntef and Yelmelon, I'm sure. So that's now part of the Weatherford Group, and they have PVT laboratories in Stavanger, United States, and the Middle East, at least. So they're a quite good laboratory. There's some new laboratories, PVT laboratories in the States. They all give different report styles. Some will give BT, some won't. Some will give gas density directly, some won't. So there's going to be probably, as many as 5, maybe as many as 10 different laboratory type reports, and each one will be a little bit different. If what I said was correct about the oil density being within a couple of percent accuracy, can we justify the lab giving us 4 decimals there? Probably not. The viscosities are given, just to go briefly, they're given in a report basically here. I know we're just about out of time. This is the last thing I'll make a comment about. Really what I want to mention, we've already talked about how the oil viscosity varies with pressure above and below the bubble point, but I wanted to mention about the gas viscosities. Of course, that's at pressures below the bubble point because there is no gas above the bubble point. Okay, but in general, no laboratories almost no laboratories report measured gas viscosities. It's almost always calculated. In some special cases, they can and will measure the gas viscosity if the gas is at very high pressures. So the Kristen field in Norway, 900 bar, I'm sure there's some measured gas viscosities out there. But basically, these are calculated from a correlation by Lee and Gonzalez. There are many Lees out there. I'm not sure which one this is, but there was a famous thermodynamicist, Professor Lee at the University of Oklahoma. Maybe it was him, maybe it wasn't. But this correlation is basically giving gas viscosity as a function of gas density and temperature. And that correlation is in Chapter 3, if you're interested. So you have to have the density and the temperature. I think that's all that goes into that correlation. And in general, you can probably expect these to be within about 5% or better. Okay, that's it. So tomorrow we'll look at the gas condensate, the constant volume depletion study, and